start my Firefox. So how do you guys like the new Firefox? I don't think that this is it yet.
Quantum or whatever?
Yeah.
I like it. I like it better than old Mozilla, and I think I like it at least on my less powerful systems than Chrome.
Okay. But most of the plugins do not work anymore. Most of the extensions and plugins, they had to rework.
I'm not super plugin reliant. So
okay.
Even on Chrome, I don't hardly use the plugins. I just like the speed of it. If Firefox could start, competing.
Oh, I do have to tell you guys that I cannot go to lab today because I have a dental cleaning appointment. So I'm going to have to cancel lab session today. But if you guys have any questions regarding the new homework assignment, just kind of let me know by email. Or we can bring it up on Wednesday or come to my office hour tomorrow, but I cannot be in the lab session today. Just dental cleaning, nothing major.
Remove all the teeth.
Do you know that you can actually have all your teeth, or if you have one tooth left, you can move it all the way from the left to the right using an orthodontic technique? Because your teeth are not actually embedded into your jawbone. Your gum is the connection piece.
There's no mechanical connection?
There's no hard mechanical linkage between your teeth and your jawbone.
Oh, that is weird.
Yeah. Well, my next door neighbor was a orthodontist, and he said, oh yeah, if you want to, and if you have one tooth left, you could move it all the way from the left to the right and back. But why would you want to do it? I don't know. Just because it can.
You're going to bring your molar right up front.
Yep. You could do that. Okay, so here's your new homework assignment. This is going to take a while. This is going to take 2 weeks. So this is a longer homework assignment. But I think this is going to be an interesting experiment for some of you, because you have not really kind of modified the architecture before. You have not gone through the whole process to do it. And I think everyone should at least go through that once, okay? Because it really helps consolidate everything that you already know about the processor and you know about programming, and it kind of puts it all into one single place. So we're going to add a new instruction. This instruction is not done yet, okay? But we'll start with this. So the new instruction is going to store the flex register into where the register D is pointing to in RAM. In C notation, this is what we are doing. We are going to dereference D as a register and store the content of flex, which is a register, to that location. This is all, okay? This is the only instruction we want to add to the instruction set. This will require a change to the architecture because currently there's no pathway between the output port, which is the Q port of flex, and the data port of RAM, okay? So this would be a good time to bring up the actual, this 3. And we want to bring up 1980. Okay, so what we're trying to do is to make a connection. I'm going to point out which two here. So we're trying to make a connection from this port, okay, to this port over here. They are currently not connected. Now, in terms of the schematic, they come pretty darn close, right? Because we are looking at this thick line here and this line over here. And you might think, oh, okay, if we want to connect those two, easy peasy. Done, not. Okay, now the yellow line is here seemingly only because the flag register only has 5 bits, but the data port has 8 bits. Okay, that seems to be the case. Okay, fine. Then we fix that. So now we go to wiring. And you will, I'm just trying to illustrate why the cheap solutions will not work. Okay, but by doing so, I'm also illustrating what would be the proper solution to this particular problem. So we're going to use a merger here. We'll have a fan out of 2 and a bit width of 8. And then we'll split it between 5 and 3, exactly. Okay, so we'll flip the direction as well. So we'll make it point west, like so. And then we'll have bits 0 to 4 coming from the register itself. And then we'll specify a 3-bit constant of 0 for the other ones. So we'll pull a constant, stash it here, make it 3-bit wide, and well, what you want to use for the constant really doesn't matter. I'm going to use 0 here. Okay, cool. Connect. Aha! Seems to work. But it's going to have problems at runtime. Why do you think this is going to have a problem when we actually run the processor? Hmm? Good. Say that one more time.
Because of bus fights, maybe?
Yep, because we're going to end up with bus fights. Very good. Okay. Because they all want to drive the bus. Who wants to drive the bus in this case? The data bus. So we highlight the data bus. Okay, we'll use this tool. We highlight the data bus and go like, okay, who wants to drive the bus? So we got the pigeon. Okay, nobody got that joke because you guys are too old to have read that storybook, but too young to be a parent who have kids who have read that book.
I know that book.
Wait, what?
You know that book?
Wait a second.
Okay, the book is called Don't Let the Pigeon Drive the Bus. It's a funny book, pretty well illustrated, but the title really is exactly that. Don't let the pigeon drive the bus. Okay, but in this case, somebody is going to drive the bus. Who's going to drive the bus here? The register bank can drive that bus. Okay? Who else can drive the bus? RAM can drive that bus. When you're reading from RAM, then the D port of RAM is driving this bus. Who else can drive the bus? So we basically have to look at the output of all the various components. Now this is not driving the bus, this is a MUX. This is the input into a MUX, it's not going to drive the bus. This is the input to a register, it is not going to drive the bus. So as far as we know, the ones that can drive the bus would be this one here. So register output 0 in certain conditions can drive this bus. The data port of RAM can drive this bus. And now we are adding one more thing, which is the flags register. Now, what is interesting in this case is the flags register lacking an independent control of when it is supposed to drive the bus is always going to drive the bus. So that means the moment I try to read anything from RAM, we end up with a bus fight. The moment we try to store something from a register into RAM, there's going to be a bus fight.
So we need some kind of separator, or probably an official term.
Yeah, so we need some mechanism so that we can say, okay, do not drive the bus unless I tell you to, okay? So of all the components that we have talked about, okay, which component do you think can be used for that purpose? We talked about this a little bit already when we first talked about RAM. It belongs to gates. Okay. So when you look at all gates, which one do you think is going to be the component that we want? A controlled buffer. Yep. So you basically need a control buffer between the output of the merger, reversal slicker, and the RAM bus. I mean the data bus. Okay? So that's the easy part. The easy part is, we just need to make this connection. We need a merger so that the width will match. And then 2, we need a controlled buffer so that we can say, drive the bus, don't drive the bus, and so on.
Is that pretty much just like a switch?
Yep. It's kind of like a switch. So when we Okay, I don't have enough room here. So the other thing that you will need to do is to make room for this to happen. And that probably can be done by moving some of these things around. So you will have to move something around to, to have enough space here. But if you pull, sorry? Possibly, okay. Okay, so when you pull a component like a control buffer, this is the input, this is the output, and this is the control. The input is just the input, okay? There's nothing really to say about the input. The control is either a 0 or 1. When the control, which is the middle point, which is the blue line here, when the blue line here is a 0, it means the output is not driven. It is just disengaged entirely. And when this pin is a 1, whatever is the input will now be presented to the output. And once again, this component has, you can let you specify the number of bits, so you have to make sure that it is matching the number of bits that you want to deal with. So, but the biggest question now is, what is going to be this control here? Okay, how do you specify this control? And we want backward compatibility. In other words, this new instruction that we're introducing cannot change the way we implement all of the existing instructions. I do not want to add anything to the ROM, okay? I can change the content of the ROM, but I don't want to change the width of the ROM. Is that okay? So that's the question. So getting back to the instruction here, I'm going to add a little bit more to this so that you know what to do with this. Okay. Call this instruction, or the mnemonics, okay. The mnemonics of this instruction is as follows. Okay, STE. Okay. Okay, I'm going to call STSP your store to the stack pointer. The flags register. Okay. I'm just trying to think of a name to call this instruction here. STF. F. Store flag. Okay. Okay. So STF is the store flags instruction. Okay, that's good. That's a good one. And we have to find an opcode for it. Okay, so how do we find an opcode? Well, what do we dig up to find an appropriate opcode? We go to the opcodes table, and then we try to find a hole or an opcode that is not in use. Okay, go to processor. Okay, so first of all, we go to the opcodes table, and then we say, okay, where can we find a spot to do this? Well, it looks like 0100 0110 is one of those spots. It's not taken up by anything, and it is available. Okay, we'll take it. Okay, so I'm going to put it here, and we'll highlight this line too, so that you guys know that we have this new instruction taking up this spot. 0100 0110 is STF or store flag. The mnemonics or the equivalent operations is whatever D points to is going to be coming from the flags register. And then over here, which is just basically comments, is to store flags to RAM where register D points to. Okay. And as promised, I'm going to highlight this with a different color so that we know that this is going to be the new instruction. And we'll find a reddish color. There we go. All right. But just to repeat this information, the opcode is a 4-6. So when we go back to the assignment, the opcode is hexadecimal 4-6. Well, you have everything that you need now to do the homework assignment. So what do we need to do in order to implement this new instruction and update the entire tool chain to make it work? Your job is to update the entire tool chain to implement this instruction. All right, so I'm going to give you an outline of what you need to update, and I'll do some of this for you too, okay? Or at least, a part of it. Okay, so we'll go ahead and use a number list here so we can refer to item so-and-so. So the first thing you need to update would be the logic sim processor schematic. Okay, I did a little bit of it. You guys have to finish it. Okay, and there will be subparts. Okay, I will even list out the subparts of what you need to do within the schematic itself. So within the schematic, you need to add a merger, which is the reverse of a splitter. You need to add a buffer. There's a specific name for that thing, controlled buffer. Okay, add a controlled buffer, which is easy. So these two are the easy parts. The more difficult part is to specify the control signal of the controlled buffer. So this is going to be a logical expression, and you have to utilize existing control lines coming out of the ROM in order to implement this. Okay?
Is this a hack, or did you design this your CPU to kind of accept this kind of modification?
It was not designed to do this.
Okay.
So we'll go through this process too. Okay, I'll give you a hint of how to do it. The second component that you need to update would be the assembler. Okay. And I'll give you an idea of how to update that too. And then you also need to update the opcodes. Okay. These are the microcode generator. Okay. All right, so how do you update the assembler? I think this part I'm going to do at least a good portion for you. Okay. So we are now adding a new instruction. When you add a new instruction, when you go to the processes folder and you double click on assembler, what are you going to do, or how do you start with this? This tab source is really whatever program you want to assemble. Obviously, it's not going to help. It's not going to help you. Source debug is only here to help you debug a program, given that you have a trace of the program counter. It's not going to help you. This tab is something that you might find useful, because this tab is listing all the mnemonic, the names of the instructions in column A. In column B, it is specifying all the hexadecimal opcode corresponding to each instruction, at least the base code of an entire family of opcodes, if it is in a family. Column C is optional, because you can see certain instructions do not have it. So column C is basically the bit position of where to find a register X. Does this new instruction STF specify one of the 4 registers? Any one of the 4 registers? Nope, it is fixed to use register D and the flags register. So we do not have any use of register C, column C. Column D is telling you how to find register Y. Oh, this is not the bit position. This is in the instruction itself. How many operands are we expecting? STF has no operands. So when an instruction has no operands, like no op or halt, then you don't specify anything in column C or column D. Column E and column F. Column E is to say, okay, do we have any immediate operands? Are we specifying a constant? No, we're not specifying constant. So column E is not needed either. Column F. Column F is the syntax of how you specify register X. Do we have parentheses going around it, or is it just register A to register D? Well, we don't have register X, so you leave column F empty. Column G specifies if we do have a register Y, what is the syntax of register Y? Do we have parentheses around register Y? We don't have register Y. Okay, so you leave it empty. There's nothing to specify here. Column H. Column H is telling you the bit position of XX. Okay, where do we find XX in the opcode? Well, it makes sense for LDI. It makes sense for compare. It makes sense for add, subtract, and all those instructions. But STF does not specify any registers. So we don't have to specify the offset, the bit offset to find the register. We don't have any YY either, so column I is not useful. And column J is not used at all. So that means to add this new instruction, all we really need to add is this. Okay, you go here, and you just specify the new instruction, and it is called STF, right? And then I protected this sheet so that I cannot accidentally make updates. And then the hexadecimal code is 4F. That's it. Now we have implemented a new opcode in the assembler. Is that okay?
Yeah, that was easy.
That was easy. Well, it's easy only because we don't have any operands. We are not specifying register XX, register YY, or there's an immediate. So that makes it like super easy. Okay. Very good.
I mean, quite literally, we could have just copied no op and renamed it.
Yep.
And I guess change the opcode.
This is the advantage of something that is what we call data-driven, as opposed to code-driven.
Yeah.
If the assembler is implemented in a gigantic conditional statement, like if string match this, else if string match that, then it's going to be quite a bit more involved. But if it's table-driven or data-driven, you just add something to the table. The only one thing I need to confirm is in the assemble tab. Okay, when it looks up the opcode, that it does look it up correctly. So one of these things is to look it up. I think it's this one here. And it looks up the mnemonics. And this should do it. Okay, so how do we test it? I claim that the assembler can now assemble the new instruction called STF. How do we test it?
Put it in.
Put it in and look at the output, right? Look at the output and make sure that it is 4.6. Okay, very good. So we go to the source, okay? Whatever is here is okay, it doesn't really matter. If you replace it with some non-existent opcode, it will complain, right? Okay, it says unknown mnemonic. Fine, okay, fine. Then we say STF, and the message goes away. Does this automatically mean it assembles it correctly? Nope.
It means it's something like something.
Yep, exactly. But it does. But when we go here, we can see that it is assembled to the opcode of 4.6 in hexadecimal. So we're good. All right. So this part is done. Cool. I just did one part for you guys. Not a problem.
Done. Just redo it.
Okay, but this is the fun part, which I'm not going to do for you, but I will tell you what to do. Because the microcode needs to be specified and I wanted the whole thing to be autonomous. Not autonomous, but it's easy to regenerate everything. Okay. So that means we have to download opcodes.zip, okay, which is a file down here. So when you go back to the processes folder, there's an opcodes.zip file. So go ahead and download it. I'm going to download it right now. So we download, and it's going to put it into the temp folder, which is fine, okay, which means I'm going to lose it after I reboot the computer. And then you go to that particular folder, and unzip it. Okay. In Windows, you don't have to do the unzip. Okay. For this to work, you might need to make sure that you have access to a bare bone type of C++ development environment. If you don't have one, I can add you to one of the servers that I have access to, so we can actually do that to the whole class. Okay. So we go to opcodes. And then we have all these files. We first say make clean. There we go. So after I make clean, all it does is to clean up all the files that can be generated. So what is left here are just the source files. So nothing more than just the source files is left. Is that okay? So what do you think is the closest instruction that you can borrow to start with this one? ST, okay, so that seems to make sense to me. So then you go copy ST, which is the source file to generate the microcode for the store instruction, to STF, or store flag. And then you take a look at stf.c, go like, okay, looks kind of like mumbo jumbo to me, but it really should not be mumbo jumbo anymore, because we kind of talked about this to prepare for your test. Yes? Okay. So the first thing you need to do, I'm going to do a little bit for you here, is you have to change this. This is reflecting the actual opcode of this instruction. So for ST, the entire family of ST instructions would have F0 as the base code. So then you have to add the individual bits of which register specifies the address and which register specifies the content. But they have the entire family is in the F0 page. The opcode that we are implementing is what again?
4.6.
4.6 in hexadecimal, so you have to change these two. The rest, I don't think you have to change. The 0 and 1 here, you do not have to change at all, because that is just specified when we talk about slice 0 of the instruction, slice 1 of the instruction, or what. So that part you don't have to change. This 2 here, I'm not remembering exactly what it does, so I'm going to go to ucode.c. Everything is in the source code here. So when you go to the swap file, if it will exist, you can delete that. And you go to write slice. Okay, XX offset, YY offset. So those are not needed. The ST instruction needs both, but this one does not. Let me switch back to the STF instruction. Okay, so the 2 and the 0, let me highlight it on this side. This 2 specifies bit 2 specifies register XX. This 0 specifies bit 0 to bit 1 specifies register YY. Do we need those two? Nope. So if I don't need those two, what do I specify here? Well, maybe we need to look at an opcode that does not use any registers. Can someone name at least one opcode that does not make use of any register? An existing opcode that we already know. Huh?
No op.
No op and halt. Okay, so those two are famous instructions, right? Because one doesn't do a single thing, the other one means you cannot do anything more after beyond this point, right? So they are significant both in that sense, right? You don't want either to appear in a normal program along the flow, but they are kind of important at the same time, okay? So then we look at no op, okay? And this is the no op instruction. So this is how we specify There's no XX and there's no YY. Is that okay? So your STF instruction also does not specify an XX nor a YY. So when you call write slice, it might look like this. Are we doing okay so far with this? Okay. Okay, switch back to this one. What about this stuff here? Each number is specifying what value we have to put into a specific bit field in the ROM to specify that slice of microcode. Okay? And these correspond to Ucode as well. So when you go back to ucode.c, the first item corresponds to microcode pointer reset. The second one corresponds to microcode pointer select. The third one is PC enable, and so on. This is where the real assignment is to figure out what value do you need to specify for each bit field in order for this instruction to work. I can give you at least 2 clues. One is we are writing to RAM. So in order to write to RAM, you have no choice but to say RAM select is a 1. But because you're using a write operation instead of a read operation, RAM load is a 0. So you have to start with those 2. But then you have to kind of hijack some of the other bits to say, oh, but we are not using register output 0 from the register bank to write to connect to the data bus. We are also not reading from RAM to one of the registers that connects to RAM, to the data port. Okay, so you have to make use of those and say, how do I specify is not one of these? Okay, is that okay? Okay, I'm going to write it down in the instruction too. So I'm going to go back to the instruction here because I know that even if I don't write it down, I'm going to forget. Okay. But I know how to do this already, which makes it kind of hard to remember what to write down here. Okay, so download opcodes.zip, unzip the archive file, copy an existing opcode generating source file to stf.c. Okay. The closest one is st, but you also want to take a look at no-op. Okay, because you're borrowing stuff from multiple instructions. Okay. Modify the calls to write slice. Okay. Update the opcodes. Modify the calls to write slice. Update the specification of XX and YY, the registers, which we talked about already, okay? And then you modify the slices, okay? You may want to borrow or at least examine the slices of other instructions, okay? Is that okay so far? Okay. And then this part is kind of the most important part, is to analyze all existing instructions and, okay, more nesting. Find out which ones can specify something to drive the data bus. What do I mean by that? You go back to the processor design itself, you click on the data bus. So I'm going to take this away because this is kind of not the way to do it, not a direct connection. So I'm going to take out the entire thing. So you have to redo this part. Okay, so you basically click on the data bus, like this one, and then you use this tool, click on the data bus, and then you basically say, okay, who can drive the data bus? This thing can. And what control signal is telling this component to drive the data bus? You look up the enable line here. The enable is this one. It's RO0EN. Register output enable. When that thing is a 1, we're definitely saying the output, or who is driving the data bus, is going to be register output 0 from the register bank. Which also means you might want to think about when this is 0, that might be a minimum requirement that we need for this opcode to specify, oh, okay, the flags register is the one that's going to drive the data bus. Okay? Then you trace this thick wire, and you go like, okay, where else does it go? It goes into the input of the instruction register, which is kind of, okay. But in order for the instruction register to update, we also need the instruction register update enable, which has no name on the schematic, but in the ucode.c, it does have a name. So when you go to ucode microcode.c, it has a name of, all the way down, it's called IREN, instruction register enable. So do you want to accidentally have your flag register to drive the data bus and update your instruction register? Probably not. Okay, so that means we want that to be a 0 too, okay? Let's see where else the data bus goes to. In other words, what we're trying to do is to say, definitely not this, not this, not this, not this, okay? All right, so we'll continue to look up, what else the data bus is connecting to. It connects to, oh, that's it, I think. Oh, wait, there's one more. It also connects here. This is also connecting to the data bus, which eventually connects to the program counter. So that means if you are not careful, you might accidentally specify a slice that will basically use the flags register to update your program counter. That may be something that you want to avoid as well. So that means you might want to make sure that this EN, oops, not this one, but this EN here is off too. Is that okay? Now when these things are all off, then you want to ask the question, do I want the ALU to be on? Well, if the ALU is on, it's actually doing calculations, right? But are you actually trying to do some calculations, or are you just trying to capture the existing content of the flags register, which is what you want? So you want the ALU to be off. Okay, very good. So we want the ALU enable to be off. This thing needs to be off. So this is the kind of exercise you have to do to kind of figure out, what are the side effects of all of the other control signals, and just isolate the ones that you need to be off, and also the ones that you need to be on, which is RAM select and also RAM load. RAM load needs to be off, on. It needs to be off. It needs to be a 0 because we are writing to RAM. Okay? So those would help you determine these the individual bit fields of slices. But then we have 2 slices, right? So when you look at almost every single instruction, there are 2 slices. Do you think how many slices do you think you need in this case?
I think just one.
Only one that is important. The second slice is just okay, let's reset everything back to 0.
Yeah.
Reset the microcode pointer back to 0, which is the same with almost every single instruction except for halt. Halt does not go back to 0, which is the whole point. Okay, so is that okay? I mean, do you guys kind of understand what you need to go through So this is really helping you understand the processor architecture itself, because it forces you to look at every single component and go like, okay, what do we want here? What do we want here? What do we want here? And so on. Okay? So are there any questions about this part?
Oh, not this part specifically, but I was just gonna ask. So we're just gonna, for when we're turning it in, we're just gonna be turning in like a file of, or a folder of all these parts, or how are we gonna turn it in exactly?
I know some people may not want to deal with the C code because you will also have to update the make file. Okay, so that's a good question. Let me see if I can answer that question eventually. Okay. So I go back to the instruction here. Okay. You also have to update the make file, which means you go back to the source here, you look at the make file, which is one thing that I'm kind of not sure about is how many people feel comfortable with changing the make file. Because what you need to do is to add a new instruction here, stf.c, and then there's one more place to add it here, is to add one more rule. Fortunately, that needs to be done, is to add stf here, but that's it. So you have to change the make file so that it will automatically try to make it. Not too bad. And so even though I'm not done with stf.c, if I say make, it will still incorporate it, because you can see at the very last stage of the make, it is utilizing stf as an executable already. It doesn't crank out the right opcode. It doesn't crank out the right microcode, okay? But it will still be something. But that's the infrastructure change that you need to make in order to do this. But the alternative is easier in some way, but kind of harder in some other way. The alternative is really just to look at the existing all.rom. In other words, you load up the processor architecture the way it is right now. You go to the ROM, right-click, edit content. You go to 460. You go to 460, which is right here. And you know the second slice is going to be 2 followed by all zeros. Okay, so just punch that in. And now you have to do all the conversions by hand. In other words, you basically just specify the bit fields, do all the shifting, convert the whole thing into hexadecimal, but it's just one location, so it might seem to be less work to some people. I don't know. Because if someone is not familiar with command line, compiling, dealing with a make file, or reading my source code, this might be more attractive, even though there's a little bit more tedious work going on, because now you have to do all the shifting, ordering all the bit fields, and then converting the bit fields into hexadecimal digits. It might be easier to some people. So I cannot say in your case which way is easier, but either way is fine. So getting back to your question of what you need to turn in. Okay. The assembler, you don't have to turn in, right? Because the only change, or the changes that we need to do to the assembler is done. So it would be kind of silly for me to require you guys to turn in your version of the assembler, which is going to be a copy of mine. So maybe I'll just require an updated ROM file. I think that's probably the most. An updated ROM file and, oh, okay, just this file itself. The new processor circ file. That's it. That should be sufficient. Okay. All right. Okay, so I'm gonna write that here. Change the style to header. A new logicsim file for the processor that, okay, put bullet points here, has the necessary circuit change and the updated microcode slice to implement the STF instruction. Okay, that's it. Just one single file, because the logisim file includes both the structural change in terms of the architecture as well as the opcode. The ROM is a part of the circuit file, so you don't have to turn in the ROM file separately. So would that make any sense? There may be multiple possible solutions, so there's no one particular way to do it. All right, so let me just make sure that everything that I need to specify are specified. The further requirement is that there should be no change to existing instructions nor their microcode slices. Okay, that's good. The mnemonic of the new instruction is STF. The opcode is 46. Okay, that's good. All right, so now that you have the homework assignment, how do you test it? In other words, let's say that you've tried to figure out, like this says 2 weeks. Okay, put it here. But how do you test it?
Try to do an operation, so you get some usable flags. Use the operation to store the flags and see if it comes up in the RAM file where you expect it to be.
Yep. Well, that will confirm the operation of the instruction that you're adding. How do you make sure it does not interfere with existing instructions?
Test all these instructions.
You have to retest all the existing instructions. Very good. Okay. So how do you retest all the instructions? Or if you are to ask someone to write a test suite of the existing instructions, how can that be done? So I'm turning your hat around. So instead of implementing something, now you're the one responsible to do QC, quality control, and you're going to test whether a new change to the processor is messing up existing instructions or not. So how do you do all that stuff? What do you think? Yep.
Take a look at the opcodes and stuff that we messed with that are very similar to what we added, but again, we modified them to implement what we needed to implement, and run those through their tests, because those are the ones that are most likely to start having issues with what we put in. Because they're so close.
Okay, but we need a kind of systematic way to do it, right, so that Okay, so how do you test the no op instruction? Or how do you define the correct behavior of the no op instruction?
Don't do
anything. So
you test it by not testing it.
All right, so let's go ahead and see how we can test it. Okay, so look at the RAM content right here. What instruction is that? The no op instruction. Very good. Okay, so if you know this is no op instruction and you know the current implementation is correct, okay, quote unquote correct, how do you track it? How do you say, now we need a record of what happens when the no op instruction executes? We go to simulate, we go to logging, right? And then what do you do? Well, sort of, okay? We kind of know that we don't have to log all the RAM locations, but but that is the complete picture, okay? If you do something like this, and you say, yeah, track out everything, and then you execute the no op instruction until you get to the next location, you save this file. You save the log file. And then every single time we make a change to either the microcode slices or the architecture, you rerun the no op instruction, and then you check the log file and make sure they are the same. And you have to do it to every single instruction, to every variant of every single instruction. That is extremely tedious if you do it by hand. So how do you not do this by hand? Now, with this tool, we can't really do it from the command line because there's no way to specify what to use to specify the RAM component on the command line. So the whole process cannot be automated, which also means I'm not expecting you guys to do it because the tool doesn't support it. If I were to ask you guys to do it, or if I am to do it myself, I'm going to go to the source code of Logisim and at least supply a way so that I can use a command line program to trigger the whole thing to execute and then generate the log file so I can automate the entire process.
And you would have to write that in C#, right?
Java. This is all written in Java. So I would have to do that. I'm not expecting you guys to do it.
Okay.
But I'm just going to do it at least once, just to illustrate the concept. So in this case, I'm going to select a file. Okay, we'll say no op test.tsv. I specifically use TSV because that's the file format that I can import into Google Sheets. Okay, save, close window, and I just need to make sure that I can get to the next instruction. So I would do a Control K. Okay, my bad. Should not specify Control K. Should be Control T, Control T, Control T 3 times. So this is way too much. Yeah, this is way too much. But that's okay. We can always just get rid of certain lines. Okay, but we'll take a look at what kind of stuff is in that file at this point. And you guys won't like it. We have 38,142 lines.
Wow.
But
You only did go through 49? No.
well, of which, how many
53?
do we actually need? Okay, so the whole thing depends on the program counter, doesn't it? So we have to look at the program counter, and basically, this is really hard to read because the program counter is all the way here. Yep. So by the time the program counter goes to 1, we can stop. We just need to make sure that it gets to location 1, and that's it. In other words, everything below this point we can erase. So now we save this file, and then we stash it, into a folder where we store the expected behavior of the no-op instruction. And then we move on to the next one, which is the halt instruction. Then we move on to the next instruction. What do you do with add instructions?
Do you have to specify a variable at some point, or?
Well, with add instructions, you have to specify values in the registers that you are adding. So your program, so this is why Logisim is not really set up to do something like this, because you cannot use a command line and say, I want the initial values of the registers to be this one, this, and that. Yep, exactly. So you cannot really, automate the text. So if you do it by hand, it is extremely inconvenient, because if you do it by hand, then what you need to do, okay, I'm resetting the whole thing. I don't think this is going to work. But if you do this by hand, then you have to go to the register bank and you specify certain values. And you have to make sure that you utilize values where the sum is different from the difference, which is different from right shifting, which is different from negation, which is different from the not, which is different from the or. Because you have to make sure that whatever you're doing is going through the adder in the ALU. Our objective is not to validate the adder itself, which is an internal component of Logisim. Our objective is to make sure that it goes through the right path inside the ALU. Is that okay?
So prime numbers?
I think certain prime numbers may work, okay? But I can point out what values would not work. 0, 0, and 0, 0 will not work, right? Because 0 plus 0 is 0, 0 minus 0 is 0. 0 right shifted by 0 is 0. 0 and 0 is 0. 0 or 0 is 0 as well. I have no idea whether the correct part of the ALU is utilized or not. So whatever you specify in these registers has to be able to distinguish and say, did we go through the adder circuit in the ALU? So that's how you design a test for the add instruction, another one for the subtract instruction, another one for the compare instruction. You go like, yeah, but if the subtract instruction is working, the compare instruction has to be working. Not necessarily, okay? So the only difference between those two is whether the result is stored back into the register or not. But the file that it would generate will be different. So you basically have to come up with a bunch of these files, and then you will need a way to test everything from scratch. Okay, every single time you make a change to the processor architecture, we go through the entire test suite and double check to make sure that the change to the processor architecture does not make any existing instruction work differently. Is that okay so far? No? Okay. Do you understand what we're trying to do?
Oh,
Not
yeah.
so much the mechanism itself.
No, I get it. It's just I'm not looking forward to it.
Not
Very
looking
deeply
forward to
now.
it. Okay. Well, I can see why, because we don't have the tools to do it. So what do you think will be needed in order to do this? Like, if this is your job, you get a job at a company, I don't know, Qualcomm, okay? And your manager says, okay, well, my brother-in-law is actually a supervisor for one of their quality control sections. So let's say your boss is now telling you, go like, okay, this is what we need, this is what we want to accomplish. Okay, every time you make a change to this part, in the processor, we want to double check to make sure that all the existing opcode are backward compatible. Okay, and this is the tool that you have. What are you going to do?
So
And quitting is not an option.
So I'm assuming that having access to it, like you mentioned, that you would have to do change Java code to let us be able to actually interface with the command line would
Yep.
be part of this.
Yep.
And follow through by maybe creating a program in C that that goes through, that can input the values, like you were saying, spit them out, and then have that generate your initial values, and another program that's essentially a modified version of the first that takes the original values and maybe bitwise compares bit by bit the output of the tested file versus the file that you output before. That's your base archive, so to speak. And if it's any different, then throw up a flag.
Yep, exactly. So if the tool doesn't support it, but it's open source, then you look into adding that option.
Yeah.
And you can potentially even add in more options, because everything has anyone opened up a circ file using a text editor just to see how a circuit is represented? It's XML. Okay, it's actually very easy to parse. Okay, so we'll go ahead and give it a try.
Huh.
Yeah,
At
it's
first, when I downloaded your circuits, it would only open as XML. I had to change the extension to .circ.
okay. Yeah, so you have the experience of opening it up using Notepad or some text editor. So what you see in that case is it's just an XML file, which is not really surprising, because XML is a very great, easy not programming, but container language to contain anything that's hierarchical. So when you look at this, okay, you look at this and go like, how is the processor, the registers, represented? Okay, so we look up. This is a register. This is a program counter. So the value, the label is the program counter. This is how we identify the program counter. We can look up the other registers. Here's the flag register. So it will specify both the location in terms of coordinate. It will specify the kind of component that it is, which in this case is a register, it will specify the width, which is the number of bits of that particular component. In this case, it's 5. And it will also specify the name or quote unquote the label of the component. In this case, it is flags. Okay, so knowing this, okay, now we can try to incorporate another input file for initialization. It's like when you load this file, also load the initialization specification so that specific components will start with specific values. Because once you have that mechanism, then it becomes possible to preload content into RAM without human interaction. You can also preload test constants into the registers, in the register bank, without human intervention. And that will go a long way to help automate the entire process. Because right now, Logisim has no capability to do any of this. There's no way to specify another file and go like, okay, use that file to specify the initial values of this particular architecture. You can't do that. So that would be something that would be usable here. Commercially, how do you think people do this? I mean, okay, I'll give you a clue. Logisim is not a commercial tool. In case you haven't noticed. So commercially, how do people do something like this? Like in the case of Qualcomm, for instance, when they redesign or they make changes to chips and whatnot, how do they do regression test to make sure that a fix to a new problem does not introduce problems on its own?
I don't know.
Oh, you don't? Okay. Well, they use.
Ship it and then wait for people to break it so then they can update the bugs, like every other software developer.
Like Bethesda. Oh, wait,
Yeah,
they
they're
don't
a
update
software
bugs.
developer. Oh, you have a problem? What a shame. We'll get on that later.
And they do not open source it, right?
Yeah,
Okay.
don't let people fix their own problems. That's the easiest way to lose money.
Well, that's what Verilog was originally designed to do. So Verilog is standardized as IEEE 1364, which is kind of significant because when it has a IEEE designation, it means enough people are using it so that a standard is needed in order to say, yes, every single implementation of Verilog is supposed to do at least this much. But let's read a little bit more.
Stable release November 2005.
Yeah, which means they got everything they needed 10 years ago. More than 10 years ago, it's already sufficient. Okay, but what is it?
Was that when we transferred over to 64-bit architecture?
Has nothing to do with number of bits. Yep, it's a hardware description language, okay, HDL. It is most commonly used in design and verification of digital circuits at a register transfer level of abstraction. What do you think we have been doing? That. Okay. It can also be used in the verification of analog circuits and mixed signal circuits as well as design of generic circuits. But the primary objective or the primary purpose of this not programming language, but it is a description language, is in the design and verification. The verification part is also a part of the name. Verilog, the veri part is coming from verification. That was the original purpose of the programming language, is for verification purposes. It's not even for design purposes, it's for verification purposes.
And logging purposes as well, it seems.
Logging, yep. I think logging and verification kind of goes hand in hand.
Yeah,
but it was
if you
not
don't verify, if you don't log it, then okay, you may have verified it, but it doesn't tell you much.
Exactly. So this is what people use in industry in order to do what we do in Logisim.
Okay.
The part that does the design is kind of interesting because this comes in more or less as an afterthought. Okay, so originally it was only used for testing purposes, but because in order to specify what you're testing, you also need to kind of specify the architecture. So that's why people started to abuse the language to also use it for design purposes. And then eventually that part became bigger than the verification part. I mean, this is one of those really kind of weird, not so weird cases actually in Silicon Valley, where something was designed for a particular thing, but then later on people use it for something else. That something else became the actual mainstream use of that original thing. I can give you many examples, but Java is one of them. Java, the programming language, the virtual machine. Okay, what do we use it now? What do you use it for? Many things, right? I can give you a few examples. Okay, I just closed it, but LogicSim is implemented in Java. Okay, on many servers, you can run Java for running backend scripts, for HTML generation and stuff like that. Java can be considered a more or less general purpose programming language. You can use it to connect to a database, extract information, generate reports, many other things. You can use it for GUI purposes. Java is really, really good at making GUI programs. But that's not what it was designed for. What do you think it was originally designed for? I see nobody bothered to look up in Wikipedia. How many people have taken the Java class? Okay. And they never talked about what Java was originally intended for?
No one cared.
Nobody cared. Well,
All this fast.
No one cared.
I think the importance of that, okay, if you look up Java, look up Wikipedia, okay, it was originally intended as a embedded processor. Wikipedia. And we want to find a page that talks about the programming language and not the implementation of it. Okay, so we want to look at the history.
95.
Huh? What?
Said 95 paragraph or two back. Right?
Okay.
Okay.
That's already after the original thoughts. The original purpose of the Java, of the entire Java tool chain was intended as an embedded processor. In other words, it was the Java virtual machine was intended to become silicon. It was never intended to stay as a software implementation of a virtual machine. It was just a transition to go like, okay, we'll test the processor using software emulation, but eventually it will be on silicon. And the Java programming language was intended for embedded processing. But then it got sidetracked, right? How did they get sidetracked? Sun Microsystem released it, and then what was the first real application of Java? Many of you are way too young to remember that because this might have happened before you were born. 95?
I was one.
Okay, a few, okay. Okay, so it was first used in browsers, like
Okay.
Firefox. Okay. So why do you
I
think it
see.
was? Why do you think it was used in Firefox in browsers?
Compatibility.
But what required that compatibility?
Well, non-compatible systems.
But what do you want to do with a browser that will cause compatibility issues?
Look at someone else's computer or look at a server. It's intercomputer communication. I mean,
Okay, when you look at older versions of HTML, what is one of the limitations of HTML?
I have no idea how HTML works at all. So
No, I keep on thinking of Flash.
Okay, HTML is great for specifying static content. Okay, I need something red over here, I need the font to be this big over here, and so on and so forth. What it is not really what it was not good at was what? User interaction. Anything that requires interaction, anything that requires cooperation from the operating system, HTML could not do.
it was good at reading and displaying, but if you ever wanted to edit it on your side,
If you want any resources, that is from the operating system, or if you want special code that will do interaction with the end user, for instance, when you type in a social security number, if you want the automatic dashes and all kinds of, all the error checking and validation, it is not easy to do back in those days. So now you have to run some quote-unquote code on the browser side in order to do stuff like that, right? To do the interaction, to do the verification, the validation, and stuff like that. What do you do? What would be the possible solutions?
Write a version for every single computer now.
Okay, so we'll first examine Microsoft's solution to that thing. It's called ActiveX. Okay, how many people know what is ActiveX?
Still around.
I certainly hope not. Okay, so the first sentence, it's kind of long, but it basically explains what it is. It's a software framework created by Microsoft that adapts its earlier component object model and object linking and embedding technologies for content downloaded from a network, particularly from the World Wide Web. In other words, this allows Internet Explorer, the early day Internet Explorer, to run custom code that is supplied from the server side. In other words, okay, you type in a URL, right? You go to a certain page. The certain page can come back with static content in HTML, graphical pages, blah, 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 blah. But it can also give you executable code to run on the PC itself. Whatever the code runs, it can interact with the browser so that you can have a two-way communication. It's doing what we use JavaScript for today. Okay?
So it runs programs within the limitation of the browser window?
Okay, so here's the problem. It does not have limitations.
Oh.
Whatever, and it is native code. It's not Java code. Okay, but that's the reason why Java came along. Two reasons. One is security. Okay, whatever code your server is sending back to your client is saying, okay, run this inside a virtual machine, inside the Java virtual machine. The code says, I want to reformat your hard drive. The Java virtual machine says, no, I don't think so. Cannot do it, right? But if you use ActiveX, it is native code that can run on the PC. It interacts with your operating system. And if you are administrator of a computer, sure, you want to reformat the hard drive, no problem, let's do it. And then you guys will be asking right away, it's like, who would be running, serving the web as administrator? That seems really kind of dangerous. Every single one who has the home edition of Windows is running as administrator. Yep, everyone is an admin for home edition.
Should always be that.
So ActiveX ended up with a lot of problems because there are people who write exploits using ActiveX, and there was just no end to exploits. And then that's only the first problem, which is security. And then there's compatibility issues. What about people using Mac OS X? ActiveX doesn't work because Mac OS X does not have the COM or the OLE framework to begin with. So it doesn't work on Mac computers. Nobody cares about Linux computers because I think they are maybe a tenth or less of the population of Mac users. So nobody cared.
Linux was around then? I thought it was just
Oh, it
Unix.
was around already, yeah, but nobody cared. But so Java was hijacked from the embedded system project in order to provide a single platform where the browser does not need to be on a particular, so that to remove the compatibility issues between operating systems. So that was one reason, or one thing that hijacked the project from Java.
So ActiveX was just too strong for its own good, and then they said
It's too flexible. It's basically
you're too useful.
flexible.
You have too many options. We have to code too much.
And you have too many security holes because of that.
Yeah.
So basically, what I'm describing is, things usually you design it for one thing, and then when somebody else finds that, oh, we can use this for something else, the other use can sometimes become the majority. Yep.
Is that why we call JavaScript what we do?
No, JavaScript really has nothing to do with Java.
But like the origin of the name, since Java did what JavaScript does before JavaScript did it? Is that why they called it that?
Possibly. I have to look up the nomenclature, like why they call it JavaScript. Yep.
So, Activex, because it ran natively, would actually be more efficient
Oh yeah.
than Java. And so we suffer the efficiency issues of Java because it was slapped in as a Band-Aid for interactivity across web browsers and servers because of its innate safety features.
More or less. But through a virtual machine, you do have a lot more protection because if the virtual machine allows it, it doesn't matter how you code your JavaScript or your Java code because it still won't let it run it. Well, these days it's actually really rare. But these days, because JavaScript has matured to the point where it can do most, if not everything that we ever need to do for user interaction, there are very, very few websites that actually require Java anymore on the client side. So Java, once again got hijacked again. So instead of doing stuff on the client side, now it's mostly used on the server side to run server scripts. So that's really kind of weird because you can see the whole migration path of how people use Java, and it kept changing. And also one of the Mars rovers also ran a Java control program, which is really surprisingly robust. I mean, the thing basically needed a reboot on Mars, and it kept running.
So what is the native operating system of the Mars rover that it's running under Java?
I can look it up. So Mars rover
XP.
in Java. Vera Sunda.
If it's running XP, we can hack it. Just
Maybe
saying.
it's Vista. Maybe it's running. That's why you always see it moving so slowly.
Okay, so here's one article on that.
Like seriously, there's an exploit for XP that lets you become a super user.
It's Spirit.
remotely.
Yeah, so right here it says the Mars exploration rover Spirit successfully landed on Mars, and Java was there too.
So what was the native operating system? Some version of Linux?
We're not. Yeah, probably.
I do not know.
All things considered, is probably Linux.
Yeah, Java has a very interesting history. So if you guys are interested, you can look into it. But it really kind of shows you how a particular concept or a particular project or an idea in Silicon Valley, once it is shared, people will find use of it and goes. Sometimes the alternative use becomes the majority, becomes the mainstream.
How strong is Java's compatibility with like hardware control? Arduino servo kind of control.
I would
With
say
a
that
robot running Java. So
it
clearly
needs an abstraction layer so that the virtual machine can talk to that. The most common way to do something like that would be through the file system. The Linux way of doing things is through files. In other words,
always.
well, it's the majority of the cases. It depends on what level of control you need. In Linux, when you see proc or sys, or dev, these are not actual files. Okay, it gives you the illusion that you're dealing with a file, but they're not actually files. Every time you talk to something in proc, it is a process, therefore proc. When you talk to sys, it is a system resource. When you go to dev, it is a device. So by abstracting an I/O device and input-output device as a file, it becomes easy for you to interact with the input-output device regardless of your programming language. All you need is a programming language that can deal with files. So you can now use what? PHP, Perl, Python, C, C++, Java, Prolog. Just about any practical programming language can deal with files. As long as you can open a file, read from it, you can read the input pins. As long as you can write to a file, you can change the output pins.
So Linux basically relies on mess with the file, close it, let someone else open it, mess with the file, close it, you open it, and then back and forth across the file.
Right, so the backend of Linux consists of what we call device drivers, or in the terms of Linux kernel, they're called modules. So these so-called modules, or what we call device drivers in Windows, is what is abstracting the actual physical device or the component into the pretense of a file. So the rest of the operating system can just look at that device as if it is just a file. Which is a very powerful technique, because now you can use just a regular, file. If this computer is, if this is an Arduino, not Arduino, but a Raspberry Pi, okay, I can do something like this to /dev da 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 da. Okay, I don't know the naming convention, but there are naming conventions. This will turn on something as the output pin, of a Raspberry Pi. I can do it on a command line. I can do it with Bash. I can do it with Perl. I can do it with PHP. I can do it with Python.
That's all handled with a file that's dedicated to the Raspberry Pi as an interaction.
Yes. So the file abstraction method is a very interesting and flexible one.
Doesn't that mean that you can turn on a camera using that same method?
Yep.
Is that not common
Remotely?
Is file abstraction not common across operating systems?
I think Windows did not have that until much later.
What about Mac? Mac's Unix. So.
Mac is Unix, so it has the same philosophy as Linux. Yep. So we digressed a little bit today, but I think it is still kind of somewhat relevant to this class. But is the homework okay so far? Do you guys know how to kind of proceed to the next stage? Okay?
You can progress. And you have the recording, right?
Yep, we got all the record. It's not even recording, it's being streamed. We are being recorded with a 20-second delay.
YouTube deals with the recording, so your resources are clear.
Exactly.
Yeah.
Yep. Alrighty. Well, wish me luck, and I'll see you guys on Wednesday. Yep.
No lab?
No lab. Got dental cleaning.
Oh, okay.
Yep. Gonna take time off for that.
Really? By the way, I'm wondering, what's the difference between AI as we would program in assembly and AI in video games? Because I understand that AI in video games, what they use is they have different nodes that they use to teach them, so they'll have pre-programmed instructions that they can use, but
Okay.
they only get unlocked